This is outcome 37, and this deals with the solubility of salts. So as of now, we have told you that all salts are 100% soluble. And this is a slight, or has been a slight, fabrication. Right now I'm going to try to tell you a little bit more of what actually happens. So we have two types of salts. One is called a soluble salt, and a slightly soluble salt. And the soluble salt is soluble. You can dissolve it in water at high, very high concentrations. These are typical salts made with elements from the 1A column: sodium, potassium, lithium, rubidium, cesium, etc. Perchlorates, ammonia, salts. Okay, any salt that has any one of these in it is typically soluble to very high concentrations, maybe greater than 10 molar. So very high, highly soluble. Okay, so that's one type of salt. The other type of salt is a slightly soluble salt. These are soluble at extremely low concentrations. We'll do an example later. If I look at a picture of a soluble salt, let me draw this. So here's my beaker with a soluble salt that I threw in. The soluble salt is down here, and this is my beaker full of water. And so what happens here is this dissolves. So I put a one-way arrow because it's 100% soluble. Then redrawing my beaker, this is what I get when I'm finished. I get a mixture of water and the salt right here. So this is my solder down here, and the big circles are anions, and the small circles, the small black dots, are cations. You'll learn more about that later. And when it dissolves 100%. Now, slightly soluble salt does a different picture. So I've drawn a picture of the slightly soluble salt. On the bottom left, here's my initial situation. I threw my salt in down here. Anions are the big ones, and cations are the small dots. And I have water in here, and it starts to dissolve. But it's only slightly soluble. So in this case, when I'm finished, only one or two or a couple go into solution in my molecular picture. Most of them stay down here in the bottom of the beaker as a solid. So this is called a saturated solution. And for slightly soluble salts, this is really easy to do. You just throw it in and it all dissolves up until it can't dissolve anymore, which is almost immediately, because very few are able to go into it. Now, you don't have to memorize these. That's a different course that you do this. But you do have to recognize from the problem for this outcome what we have in there. Okay, so now I'm going to do two different problems here, one with the soluble salt and one with the slightly soluble salt. So a soluble salt, I'll do it first. So let's take sodium chloride. That's a soluble salt, almost 100% soluble. And I'll throw 116.88 grams into 1 liter of solution. And I want to calculate the molarity of the solution. So if I do that, that's really easy to do. I have 116.88 grams. All of it dissolves, so it dissolves in 1 liter. So I'll put it all in 1 liter, and I'll convert that to molarity. The molar mass of sodium chloride is 58.44 grams of sodium chloride per mole of sodium chloride. And I get the molarity, which is 2.00 molar sodium chloride. Very easy. All of you should be familiar with this. Okay, that's the first problem. You're not going to have to do this. You know how to do this already. The next problem is a slightly soluble salt. In this problem, I take 116.88 grams of silver carbonate, Ag2CO3. I'll write that again, Ag2CO3. Now, the problem here is it doesn't all dissolve. It's a slightly soluble salt, so I want to figure out how much of it does dissolve. Okay, so the first step here is to write the reaction. So the reaction we write for a slightly soluble Ag2CO3. Now, since it's slightly, which means it doesn't all go in, we put the double arrow, dynamic equilibrium. And I get 2 silver pluses and 1 carbonate. You need to be able to figure that out. Aqueous, aqueous, and over here I have a solid. That's important. So now I do an ice table. Again, you're familiar with this. And silver is an infinite supply of it because it's sitting on the bottom of my beaker. So I put a dash like we do, 0, 0, initial. Then X of the silver carbonate reacts. So X, and it's minus X, excuse me. This gives us X, but there's 2 of them up here. So it's 2X. Be careful with that. And an X over here. So when I'm done at equilibrium, I have an infinite supply of silver carbonate because only a very little bit of it dissolved. I have 2X down here and X here. The equilibrium expression you should be able to do, and it's given a special equilibrium symbol, KQ, which is now called KSP. Sometimes called the solubility product. You don't need to know that. But it's equal to the equilibrium expression for this reaction, which is going to be the concentration of the products, Ag plus squared times the concentration of carbonate. Now it's squared because I have this 2 up here. Don't forget about it. Divided by the concentration of silver carbonate, which is a pure solid. Any pure solid or pure liquid goes to 1. So I get, let me write it down here in the left hand corner, KSP is equal to the concentration of silver plus squared times the concentration of carbonate. You've got to have charges on these. Don't forget them. Don't care about the phases up here. I mean, you need to know them, but I do care about charges. Okay, let me erase. So there's my situation. I now have my equation, and I plug in my variables. So I get KSP, and for silver I have 2X right here. This is the place people make mistakes, so it's equal to 2X, and then I got to square all of that, not just the X. It's the total concentration of silver squared times the carbonate, which is easy enough, it's X. And so that's highly soluble. You can look up the KSPs and we'll give you tables for them. There's tables in Sapling. So the KSP for this thing is, KSP is equal to 8.46 times 10 to the minus 12th. Okay, so when I combine that, I get up here 8.46 times 10 to the minus 12th equal 4x cubed. The 4x cubed is coming from here. It's 2x squared times x. So when I solve this, I take x is equal to the cube root of 8.46 times 10 to the minus 12th divided by 4, which gives us 1.28 times 10 to the minus 4th, and the units are always moles per liter. It always comes out in molarity. The units here, you notice I've kind of ignored them. KSP is done in molarity. You don't have to put any units in, but you have to recognize that X is in molarity. Now when you give your answers, you will give molarity. So I'm going to give them answers on the next slide. Let me erase some. Okay, so I have X is equal to 1.28 times 10 to the minus 4th moles per liter. So what is the solubility? This is a solubility. So the units will be, the solubility will be equal to 1.28 times 10 to the minus fourth moles of silver carbonate per liter solution. The concentration of silver plus will be equal to 2x, which is equal to 1.28 times 10 to the minus fourth times 2, which is equal to 2.56 times 10 to the minus fourth moles of silver plus per liter of solution. And finally, wow, I run out of room again. Let me erase a little bit more. The concentration of carbonate, which is just X, I'm getting that from these things, is equal to 1.28 times 10 to the minus fourth moles of carbonate per liter of solution. And we're done. That's your problem that you're going to have to do. You have all the skills to do this.